Okay, people, let's get started. So please turn on your video if you're comfortable with it. Otherwise, get ready with the icons. All right, so unless you have particular things you want me to talk about, my plan is to continue going through sections as quickly as possible, doing a quick review of the main ideas, doing maybe one example per section. So I'm gonna keep going with this. Speak up, interrupt. If you have any questions or you want me to work on something specific, or put it in the chat and other people can tell me about it. All right, so we got to the point of integrating, or we got to the point where the next section was integrating rational functions. So what is this section about? So it's when we have rational functions which are the form of this, p of x over q of x, where p and q are polynomials. And we say it's proper if the degree of p is less than the degree of q. And if it isn't proper, we can do long division to turn it into just a polynomial plus a proper rational functions. And then we have to consider various cases based on what form the denominator takes. So we had 4 cases to consider. So case 1, if q is the product of distinct linear factors. So q of x, say, is a1 of x plus b1 times a2 of x plus b2, and so on like this, right? And in that case, then we can write p of x over q of x is equal to, say, a1 plus a2 like this, however many there are. Suppose we have r factors. Like this. And then the trick is to actually find these coefficients, a1, a2, a3, and so on up to ar. Because once we've done so, each one of these individual things are easy to integrate. Yeah? So I'm going to quickly run through the cases and we'll do an example. So case 2 is when we have repeated linear factors. So these are when we have distinct linear factors. Okay, so we have something of the form of q of x is equal to some stuff, but then there is, say, this ax plus b to some power, let's say r, and then some other stuff. Yeah? Then, in order to account for this ax plus b to this power, we have to put in the mix things like this, a1 of ax plus b to the power 1 plus a2 ax plus b to the power 2, and so on. All the way up to whatever power we have with this repeated factor. Okay. Case 3 was when we have an irreducible quadratic, right, in the denominator. So q of x contains whatever stuff, but it also contains something which we can't split into factors, linear factors, so something like this, where we can't break this thing up. This thing doesn't have real roots. We can't factor it. Speak up. Didn't hear whatever you said, so I'll say that again. I'll put it in the chat. So this is an irreducible quadratic. So then to deal with this, we have to introduce something like this, ax plus b over this irreducible quadratic. And case 4 is when we have irreducible quadratics to some power. And I'm not going to write that down because it's pretty unlikely you see this. But that's where you have the similar thing, but you're going to have to put okay, actually, I'm going to write it down. Easier to write it down than try and explain it in words. So we have q of x equals ax squared plus bx plus c to some power. And then it's sort of similar to case 2 in that we have to put in these coefficients dealing with each one of these powers. So we're going to have a1, let's put this capital B, over the first power. And then over the second power, and so on, however many powers they are. So it's kind of analogous to case 2. And this is the hardest case, and it's the least likely, but it's not impossible that you see this. Okay, cool. So these are the 4 cases. And in every case, the game is the same. Once you have this representation, so look at this representation. Once you have this representation, we're going to make the denominators the same, and then we're going to try and find out what the coefficients a1, a2, a3 is based on the fact that the numerators will therefore also have to be the same. And that will mean that there'll be an equality of some kind of a polynomial, quadratic or cubic or something, where we have to solve for the coefficients, and I'll show you. So suppose we have this thing. X squared plus 2x minus 1 over 2x to the 3 plus 3x squared, that's a 3 there, minus 2x dx. So first note, it's proper, so we don't have to do any long division. And second thing to note is that this bottom thing can be factored, so we can factor out an x straight away. And if we factor out an x, we can also see we can factor the denominator. It's going to be 2x minus 1 over x plus 2. So this thing turns out to be the denominator. So it's 2x to the 3 plus 3x squared minus 2x. So these are distinct linear factors, right? So we write x squared plus 2x minus 1 over x, 2x minus 1, x plus 2, and this is a over x plus b over 2x minus 1 plus c over x plus 2, right? That's what the theorem says. And then we make the denominator the same in order to try and find these coefficients, right? So let's multiply top and bottom here by x minus 2, x plus 2 to make the denominator of this expression the same as this one, right? So if we do that, we're going to have, 2x minus 1, x plus 2, and then the denominator is the same. So we're going to put the denominator the same everywhere. Let's do the same for this guy. We need to multiply by x, x plus 2, so bx, x plus 2. And let's do the same for this guy. We need to multiply by x, 2x minus 1. And the denominator is the same. It's this thing, x, 2x minus 1, x plus 2, right? This thing is the same as this thing. Everybody with me? Give me a thumbs up if so. Okay, cool. So the only way that's true is if when we multiply by the bottom, then the top line is the same, right? So we have x squared minus or plus 2x minus 1 is this thing. And let's start to multiply this out because we're going to be comparing coefficients. So what we have 2x squared. We're going to have a minus x and then a plus 4x. So it's going to be plus 3x. And we're going to have a minus 2 right here. For the b, we're going to have an x squared plus 2x. And for the c, we're going to have a 2x squared minus x. And then we're going to compare the powers of x, right? So we're going to put all the x squareds together and compare that coefficient with the x squared coefficient over here. So we're going to have a 2a from this thing. We're going to have a b from this thing. And we're going to have a 2c from this thing. Yeah? And let's compare the coefficients with respect to x. We're going to have a 3a from this thing, right? We're going to have a 2b from this thing. And we're going to have a minus c from this thing. Yeah, that's coefficient in x. And finally, the coefficient in just the constant. And there's only one constant, it's just this minus 2. So we're going to have just minus 2a. So what we have is that this quadratic is equal to this quadratic for every single x. Yeah? Yeah? And the only way that's possible is if all these coefficients in front of the quadratics agree, right? You can just, I mean, we haven't explained, look, go back if you're not sure about this, but you can just look at it, right? So if we have two quadratics, the only way they agree for all possible x is if the coefficients in front of all of them are the same, right? If any one of these coefficients is different, then they can't possibly agree. Yeah? So that means that we have 1 is equal to 2a plus b plus 2c. That's the first equation. Second equation is that 2 is equal to 3a plus 2b minus c. And the third equation is that minus 1 is equal to minus 2a. Yeah? So we can read off straight away what a is. A is 1 over 2. And then we have to try and solve for these b and c from these other two equations. So we have 3 equations, 3 unknowns. Often that's enough. So later you'll learn a subject called linear algebra, which tells you exactly when you can solve these kind of things and gives you a very slick way to do it. But right now we're just going to mess around by hand. So let's call this equation by star. Any example you have of this isn't going to be particularly hard. Let's multiply everything here by 2. So I have a minus 2c, because my plan isn't going to add it to this one to kill the 2c. So I have 4 equals 6a plus 4b minus 2c. Right? So let's take this guy and let's add it to star. So let's call that, I don't know, star, star, star. So it's a good idea to sort of do this so that you remember what steps you've done, so that when you're checking, you can verify more easily if you see what you've explicitly done. So we have 8a, and then we're going to have a plus of 5b, and then the 2c's cancels. That's the point of doing this. 8a, we know what it is because a is a half, so that's just 4 plus 5b. And then put this on the other side, so we have that 5b equals 1, which implies b equals 1 over 5. Right? And then we can put that into any one of our equations to find c. Let's put it into star, star. So we have 1, a is a half, so this is 1, b is 1 over 5, and then there's 2c. So I put this over on the other side. We're going to have minus a fifth is 2c, which implies c is minus 1 over 10. And then we're all set, right? Because now we have the representation. So this thing, let's call this equation star, 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 star. Okay, so then star, 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 star is now equal to, we just put in the coefficients. So a was a half, right? So we have 1 over 2x, and then b was a fifth, right? So we have 1 over 5 times 2x minus 1. And then c was minus a tenth. So we have minus 1 over 10 x plus 2, and all of these things we can integrate, right? So the antiderivative of star, 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 star is the antiderivative of all of these things, so it's going to be 1 over 2 log of x. We ask ourselves, what's the antiderivative of this thing? Well, if we try and put in log of 2x minus 1, we don't quite get the right thing because of having the wrong constant in front, because when we differentiate this, we are going to get 2. Let me show you what I mean. So look, if we differentiate log of 2x minus 1, then by the chain rule, right, it's we differentiate the outer function, leave the inner function alone, right? And then differentiate the inner function, we have 2 up here. So we are off by a factor, right? What we'd like to have is a fifth, and instead we've got 2. So if we just divide both sides by 1 over 10, then we get exactly what we want, right? Then we get 1 over 5, like this, which is what we want, right? So that means that the antiderivative we require is going to be 1 over 10 log of 2x minus 1. And the same story for this thing. What we need is minus 1 over 10 log of x plus 2, and then there's a constant c right here. And that should be it. Everybody happy? Yeah? All right, so all these other cases is exactly the same. You set it up this way, you make the denominator the same, you create some equality between the numerator and the numerator on the right-hand side, which is made up of your coefficients, and then you put the right-hand side as whatever polynomial you have, the first power, the second power, the third power, and then you read off these 3 equations that you have. Yeah? And then it's just solving these equations. So it's kind of a lengthy problem sometimes, but it isn't actually conceptually hard. All you need to do is set it up like this, and then everything you're doing from this point onwards is just completely common sense, right? There's no other reasonable way to go. There's no kind of choices here. From this point on, it's just like a straight, it's a straight road, and you just have to go down the straight road and try not to make a mistake. Yeah? And if you do make a mistake, and this is a free response, it's not going to kill you. What we're looking for is that you know actually how to do it. You know the steps. Okay. Cool. Before I erase, everybody happy? Any questions? Give me a thumbs up if you're okay with this. Just going to move on to a new topic. Cool. All right. Is strategy for integration. So this is like 7.5, I think. And so there is no just follow the steps type algorithm to teach you how to do all these integrals. You have to just go into these problems with your set of tools and then just try things, and maybe you get somewhere and maybe you don't, and then you backtrack and you try something else. It's a kind of an art how to do these things. But there is a basic kind of outline you can attempt to do. So the first thing to do is to try and simplify. So it could be that with some algebra, the problem becomes easier. So before you get to work with any difficult, complicated methods, just check that there isn't a way to reformulate it into an easy question. Second thing to do is, or the second simplest thing is to try U sub, which often makes things somewhat easy. And then the third thing is to classify what a question might be looking for. So it could be an integration by parts. So you could see that you have some product of functions f, g, where if you write one as u and the other one as v prime, then instead of looking at u, v prime, looking at v prime u, you have something better. Then that's the method to do. It could be that you have a trig integral. If it's a trig integral of some kind, product of sines, cosines, product of sec and tan, then again, you know what to do. It could be something that requires a trig substitution. You could be looking at something which has somewhere inside it something like this, where it can't be done by doing a U sub. It could be a rational function. So it could be clearly one of the specific methods that we've taught you. And if so, go ahead, use that method. And then if after doing that you don't see that it's one of those things, then you could try and do a U sub and then look if the new form of the thing is in one of the forms that you recognize. But basically at this point you are now going to have to get creative. So if after doing these three things you can't classify, then it's a matter of turning the problem around, doing a U-sub, maybe doing an integration by parts, changing it in some way so that you see what form you can take it into. And doing that is just a matter of practice. If you look at the end of the section, there's a whole list of problems. All of them are just given to you without saying what method to use. An excellent practice for this is to go through the odd ordered exercises and just do them and just see if you can find the methods to do this. And you'll find that if you practice this, you will rather quickly, your brain will pick it up. It will find the method to do the correct integration. You will be able to do these things. So this is the kind of culmination of the integration techniques. It's actually really good practice to go directly to 7.5 and just do as many of the auto exercises as you can, and you should be able to do them. If you can't, just bring them to me in office hour. We'll go through them together. Okay, so after that, we're going to go to 7.8, which is improper integrals. And there are two types. There's type 1, where we have an integral from some number to infinity, f of x dx, or from minus infinity to some number, f of x dx, or from minus infinity to infinity. Okay, so we're going to start with considering this guy. So we define the integral from a to infinity f of x dx to be the limit as capital R tends to infinity of a to r f of x dx. And if you think about it, that's the only thing it can mean, right? Because if we consider what this is the area underneath the graph from some number a all the way to infinity, right? And there's no way to explicitly evaluate that with fundamental linear calculus because infinity is just not a number. But we can certainly evaluate it from a up to r, right? And if, as we let r tends to infinity, this thing is more and more consistency like this thing, then that's the meaning of this. There's no other reasonable way to define this, right? So if you were writing a computer program and you were tasked with calculating this integral, I mean, you can't put infinity into the computer, right? But you can put any number into the computer. So what would you do? You would say, okay, I'm going to integrate from a to r, where r is a very big number, and I'm going to let r get as big as possible, as big as the computer can handle, right? Yeah. But we have something better than computers. We have our brains. We can actually determine this not just for some large r within the memory capacity of the computer, but for any r, and by the concept of limit. And if this limit exists, that's what we define this to be. Yeah? And that's the only thing it can be. Yeah? And we define the integral from minus infinity to a. Let's call it g this time in a similar way. That's the limit as, let's say, s goes to minus infinity of the integral from s up to a g of x dx, right? And the integral from minus infinity to infinity is when we take any point, any number between minus infinity to infinity, and we just sum these two integrals. So what I mean is this. So this thing is the integral from minus infinity to a h of x dx plus the integral from a to infinity h of x dx. That's how we're going to define it in Calc 1. Later, as you do more maths, you'll find that there's better, more sophisticated ways to define this, which allows you to evaluate more integrals, but that's what we're doing here. Okay, so if we do this, then we need to see how we can calculate these guys, and there's a key example. So there's a key example, which if you understand it, kind of contains most of what you need to know, is this integral from 1 to infinity 1 over x dx. So if we try and evaluate this, this is the limit as r tends to infinity from 1 to r, 1 over x dx, and we can, having pen problems, figure this out. This is the limit as r goes to infinity, and then we go from 1 to r, the antiderivative is log of x, so what's this? This is the limit as r goes to infinity of log of r, log of 1 is just 0, so that's infinity. So that thing has infinite area underneath its graph, right? So why is this the key example? This is the key example because this thing only just fails. This thing only just fails to have finite area underneath its graph. If we consider something that is going down to 0 just a little bit faster than 1 over x, so for example, consider f of x equals 1 over x to the p for p bigger than 1, right? So if p is bigger than 1, then x to the p is bigger than x. So 1 over x to the p is less than 1 over x, right? So the graph of this guy lives under the graph of 1 over x, right? So this is 1 over x, and this is f, and it's just a little bit under, right? So p can be incredibly close to 1, but it's still bigger than 1, so it's just squeezing a little bit under. But this thing, when we integrate it, we find that it has finite integral, right? Because if we integrate from 1 to r, 1 over x to the p dx, what is that? That's x to the minus p, right? And then what's the antiderivative? The antiderivative is x to the 1 minus p over 1 minus p, like this. And I'm running out of space. Put it up here. So I'll call this thing star. So what's this? This is 1 minus p r to the 1 minus p minus just 1, right? And p is a bit bigger than 1, so r to the 1 minus p is r to a negative power, so it's going down to 0 as p goes to 0, right? So since p is bigger than 1, this 1 over 1 minus p is negative, so let's turn it around and make it positive. So we have it like this, and then we'll swap around these things. So 1 minus r to the 1 minus p, and let's actually write that as 1 over r to the p minus 1, like this, right? And this is going down to 0 as r goes to infinity, so this thing actually converges. So the limit as r goes to infinity of 1 to r of 1 over x to the p dx is just going to be, this thing vanishes, it's just going to be 1 over p minus 1. Now, and notice as p gets closer and closer to 1, this number gets very, very big. So it's blowing up to infinity as p tends towards 1, which is what we expect, because when p is actually equal to 1, it is infinity. Yeah. So everything is consistent with our pictures and with our calculations. Yeah. Cool. So the moral, 1 over x is not going down to 0 fast enough for it to converge. If we take it a little bit faster going to 0 with p just bigger than 1, then it will work. Then it will work. Yeah? It will work. Later, when something we talked about is that even if we take it going down to 0 just a little bit faster by something like this, this thing will still actually converge. So this is so much just on the edge of converging. And we say it converges because this limit has to converge for this to have any meaning. Yeah? So we can quickly understand a lot of these improper integrals just by comparing them to 1 over x. If they are going down to 0 faster than 1 over x with some kind of a power, if they're going to 0 like 1 over x to the p, then we're going to be okay. And if they are not, then it's not going to converge. Yeah? So that's what I want you to do before doing any calculations. Just ask yourself, is it going down to 0 fast enough? And then, based on what you think the answer to that is, do the calculation and see if that can. Okay. So, improper integrals of type 2. So this is where we have a vertical asymptote somewhere. We want to find the area underneath the graph as we integrate from whatever number a up to the improper, up to the vertical asymptote. Right? And again, we can't do this by just plugging in the value at b because the function's infinity. Fundamental theorem of calculus, our main tool to explicitly calculate these things, only allows us to use this for functions that are continuous. At least that's the theorem we presented to you in this course. It's true in more generality. You'll learn this later. All right, so for this case, we can't just integrate from a to b. It makes no sense. So we're going to do the same strategy. We're just going to stop a little bit short, right? We're going to stop a bit short of the b. Let's call that r, right? And then we consider the area underneath the graph, or the signed area underneath the graph from a up to r. And if, as we let r go up towards b in the limit, this thing tends to a consistent answer, then we say, okay, that's what we define the improper integral of type 2 to be. And again, that's the only thing it can be. That's the only reasonable way to define it, right? So if f has a vertical asymptote at b, then I've got to define the integral from a to b, f of x dx, to be the limit as r goes up to b. So it's going up to b from the left-hand side, so I'm going to put b minus here, of the integral from a up to r, f of x dx. And that's all it can be. Yeah? And the same thing if we go from the other side, so if we want to integrate from c to b, then we're going to have to take the limit s as s goes down towards b from the right-hand side. Yeah? The picture just shows us that's the only thing can be. And so the integral from b to c, so here b is the bottom limit of our integral of x dx, has to be the limit as, let's call it s, that is s this time. And now we're going from the right-hand side, so we're going to write b plus the integral from s to c f of x dx, if these limits exist, right? And then we say it converges. So if these limits exist, we say the integral converges. All right, so again, the key example is 1 over x. Because if we look at 1 over x, it's definitely got a vertical asymptote at 0, right? And let's see if this thing actually converges. So let's do this calculation. So we're going to take the integral from 0 to 1 of 1 over x. This thing means the limit as s goes to 0 from the right-hand side of the integral from s to 1 over x dx. Yeah? And this thing is equal to the limit as s goes to 0 from the right-hand side. And the antiderivative again is log, so we have log of x, like this. And then what's this? This is the limit as s goes to 0 from the right-hand side. So log of 1 is 0, so we have 0 minus log of s, right? And as s goes to 0, log of s goes to minus infinity, so this thing is actually going to just be infinity, so it doesn't exist as a number, right? So we have infinite amount of area underneath the graph. And we started at 1, but we could have started at any number, it doesn't matter, right? There's infinite amount of area underneath the graph of 1 over x from 0 to anything. Yeah? So this thing does not converge. We do not have enough. We do not have this thing. We do not have this thing is is blowing up slowly enough. This thing is blowing up so fast as we go towards 0 that the area underneath the graph is infinite. Yeah? Okay, so now we just change this slightly and see what will happen. So if it blows up faster than 1 over x, for sure it's not going to have finite area. Yeah? So we want to see what happens if we blow up slower. Yeah? But if we try and figure out what happens when we blow up slower, then we have to take a power of x which is less than 1. Right? So if we consider integral from 0 to 1, 1 over x to the q dx, dx, where q is now less than 1, then we might have a hope. So there's no point taking q bigger than 1, because if q is bigger than 1, then x to the q is smaller than x, because we're considering small x. Yeah? So x to the q is smaller than x. So 1 over x to the q will be bigger than 1 over x, and therefore it can't possibly converge, because it's going to be above this graph. So now the only chance we have would be when we take q to between 0 and 1. Yeah? Because if we have q between 0 and 1, and x between 0 and 1, right? Then x to the q, it's a root power of q, right? So it's actually going to be bigger. Start again. It's a root power of x, so it's actually going to be bigger than x. Yeah? So for example, if q was a half, right, and x was a quarter, yeah? So what's the square root of a quarter? Square root of a quarter is going to be a half, because a half times a half is a quarter. Yeah? So when we take a root, a power which is less than 1 of a number which is less than 1, then it's bigger than what it was. And even better than that is to have the picture in mind, right? So we know what the graph, the square root function looks like. It looks like this, yeah? It curls like this. So this here is 1, right? So if we compare just y equals x, so this is y equals x, and this would be, say, x to the q, where q is less than 1, then we see that x to the q is bigger than x if q is something between 0 and 1. Yeah? So root powers make things bigger when we have small numbers. This is a key point, and this is a key point of confusion. Last time, when we had type 1, then to get the thing underneath the graph, we took p to be bigger than 1. Now we take q to be less than 1. Thumbs up if this point is clear to you. Okay, cool. So we might have this will work for q between 0 and 1, because then we have that 1 over x is bigger than 1 over x to the q. So 1 over x to the q lives underneath the graph, right? So 1 over x to the q lives underneath like this. This is 1 over x to the q. Huh? So it might work. It might have finite integral, and it turns out it does. We could just calculate it. So then the integral from 0 to 1 of 1 over x to the q dx is the limit as s goes down to 0 of s to 1. Let's write this as x to the minus q dx. And that's the limit as s goes to 0 for right-hand side. And what's the antiderivative of this? It's going to be x to the 1 minus q over 1 minus q, right? If we differentiate this, we get this. Yeah? And then we put in the limits. Let's put it down here. So that's going to be 1 over 1 minus q. When we stick in x is equal to 1, the limit sign, so this is the limit as s goes to 0 from the right-hand side, 1 over 1 minus q minus s to the 1 minus q over 1 minus q. And since q is between 0 and 1, 1 minus q is a positive number. So as s goes down to 0, this thing vanishes. So this is just equal to 1 over 1 minus q. Yeah? Which is a number, which converges. So then this integral indeed does have finite area underneath its graph. It still has this vertical asymptote, right? Still blowing up pretty fast, but it's not blowing up so fast that the area underneath it is infinite. The area is finite. Yeah? So it's a key example, just like 1 over x was a key example for type 1, because it only just fails to converge, right? So 1 over x, as we went from 1 to infinity, only just failed. And if we had something in a power way that was underneath it, it would work. 1 over x from 0 to 1, again, is the key example, because if we have something which is underneath it in a power way, you know, then it will work. Then it will work. It will converge. You know? And just as before, if we take q towards 1, then this thing is blowing up towards infinity, which is what we expect, because when q is actually equal to 1, it is infinity. So everything is consistent. Everything's making sense. Huh? So the key thing you have to take away is this example from 1 to infinity and the same example from 0 to 1, and ask yourself, do you have something which in a power way, in a power law way, is going to be underneath your graph? No? And in the case of improper of type 2, when we have a vertical asymptote, that means considering something of the form 1 over x to the q, where q is something between 0 and 1. No? So this isn't particularly hard if you have these pictures in mind. Yeah? If you have these pictures in mind. Yeah? Cool. Everybody okay? Everybody with me? Yeah? I am over time, actually. Okay, so probably this is a good time to wrap up. Please, if you haven't put in the chat what you consider to be a hard topic, put it in there so I have some idea. Also, feel free to email me about this. Keep reviewing from the start this course. Do the past practice, do the past midterms, another excellent way to revise, and focus on your weaknesses. Do the odd-ordered exercises in the sections you find particularly hard. Come to my office hour with things that you struggle with. We'll talk about it. And keep momentum for the last bit of this course so you can finish strongly. All right, great. So have a great weekend, and I will see you all on Monday. Bye-bye, people.